On the instrument panel of a jet aircraft surrounded by pressure sensors, weather radar, and satellite navigation computers, you will still find a unit that sounds as if it belongs to a centuries-old sailing ship, the Knot. Its presence feels slightly out of place, as though aviation has reached the supersonic age while quietly carrying a memory from a wooden sailboat. Yet when we trace its history, we discover that the Knot is not an outdated relic. It is a crucial clue to understanding how aviation built its navigation system. Strangely enough, to understand modern flight speed, we must return to the image of a rope slipping through a sailor's hands hundreds of years ago. Aircraft do not use ropes, nor do they have water to create resistance. But pilots share the same fundamental needs sailors once had. They must measure motion across a curved surface. Even though airplanes move through three-dimensional space, their routes are projected onto maps of latitude and longitude. When a pilot adjusts heading, they are working within a coordinate system originally refined during the era when maritime trade dominated global movement. In the early days of aviation, engineers saw no reason to invent an entirely new navigational framework when an existing one had already proven stable for centuries. The nautical mile, defined as 1 minute of latitude, became the natural unit for measuring distance. Once distance is measured in nautical miles, speed must logically be expressed as nautical miles per hour. That unit is the knot. The overlap between sea and air is not coincidence. At a deeper level, both systems rely on the same spherical geometry of the Earth. Had aviation chosen the statute mile instead, navigation calculations would have drifted away from Earth's geometric structure. The mile works comfortably on flat maps. But aircraft do not fly across flat plains. This is where the rope leaves its invisible imprint on modern airplanes. The rope itself never left the sea, but the mathematics encoded within it followed aviation into the sky. Centuries ago, sailors threw a wooden block into the water and counted the knots that passed through their hands over 28 seconds. Each knot represented a fraction of a nautical mile per hour if the vessel maintained its speed. That measurement was standardized according to Earth's curvature, because the nautical mile directly reflects the length of 1 minute of latitude. When aviation emerged, engineers searched for a unit that could integrate seamlessly into calculations involving flight paths, banking angles, crosswinds, and destinations. They recognized that the rope-based system had already linked geography and time into a single quantity. Measuring speed in knots meant that aviation charts and maritime charts could share the same reference grid. This compatibility proved especially valuable in the early decades of flight, when pilots still relied heavily on paper maps and mechanical plotting tools. The transfer of navigational knowledge from sea to air happened smoothly because both industries spoke the same geometric language. Eventually, pitot tubes replaced floating wooden blocks. Dynamic air pressure replaced water resistance. Flight computers replaced sandglasses. But the final output remained knots. The answer to the question, why not use km, h, or mph, lies in geometry rather than tradition. Kilometers per hour fit neatly within the metric system, and miles per hour remain common on highways. Yet, neither unit aligns naturally with the latitude-longitude grid that governs global navigation. The knot does. A pilot cruising at 35,000 feet may have a digital map updating every second. Yet the core problem remains unchanged from centuries ago. Determine position on a moving fist. Curved surface. Every airway and waypoint is anchored to the global coordinate grid. That grid functions most efficiently when distance is expressed in nautical miles. Speed in knots allows pilots to estimate arrival times, calculate wind correction angles, and plan fuel consumption without constantly converting units. Air traffic control also standardizes speed reporting in knots. This consistency reduces communication errors, one of the most critical factors in aviation safety. If one aircraft reported speed in miles per hour and another in kilometers per hour, pilots and controllers would be forced to perform mental conversions in situations where time and clarity are essential. There is another layer to this legacy. Flight paths are rarely straight lines in the geometric sense. On a flat map, the shortest route appears as a straight line drawn with a ruler. On a spherical Earth, the shortest distance between 2 points is an arc known as a great circle route. Nautical miles and knots are inherently compatible with spherical geometry, which makes them naturally suited to these curved paths. When a flight travels from Tokyo to Los Angeles, much of its journey follows such a great circle arc, guided by the same mathematical principles once approximated by knots on a rope. Pilots no longer measure speed with hemplines and drifting wood. Yet they still rely on the unit born from that method because it reflects the true shape of the planet. The knot survives not because of habit, but because it unifies motion, time, and geography into a single coherent measurement. Technology can evolve dramatically, but the mathematical framework beneath it is far more resistant to change. The numbers glowing on a cockpit display today are refined descendants of a method once based on seawater, drag, and coarse rope, and each time a pilot reads 470 kT. They are continuing to solve a problem, first approached by a sailor casting a block of wood into the ocean. If you enjoy uncovering the hidden engineering logic behind technologies that seem entirely modern, there are many more traces to follow. Some of today's most advanced systems still rest on ideas formed in eras when materials were scarce, but geometric reasoning was already powerful enough to shape the future.